Yep. Thank you very much, JB. My name is William Dezek, but most people call me William or Bill, so just call me Bill. Our next presentation is called Mean Flow Effects on Hypersonic Boundary Layer Stability Analysis using LastTrack. I could see your presentation, Xiaowen. I'll read your bio that you have right now. Dr. Xiaowen Wang is a research engineer at National Institute of Aerospace. His research interests are thermal, chemical, non-equilibrium flow simulations, hypersonic boundary layer stability analysis, and transition control.
Thank you, William, for the introduction, and good afternoon, everyone. The title of my presentation is Mean Flow Effect on Hypersonic Boundary Layer Stability Analysis using LastTrack. My co-authors are Qiaolin Chen and Fei Li at NASA Langley. I will start with a brief introduction to the LastTrack code. So LastTrack is a publicly released code. It's for hypersonic boundary layer transition analysis. The code is developed by Qiaolin Chen in early around 2000 years. So the first version of the code is for perfect gas. So with the development of the code, of course, for hypersonic flow, such as the reentry vehicles, the chemical reactions, and the non-equilibrium effects becomes very important. So the further development of the code is to include the capability of non-equilibrium flow effects. Currently, LastTrack is capable of analyzing linear instabilities for non-equilibrium flow. So essentially, linear instabilities here means you either use the linear stability theory or use the linear parabolized stability equation. So these capabilities, they will come, they are available in the coming third version of the code. So with that, the objectives of my task is to, at first, to complete the implementation of the code, essentially for the non-linear PSE method in the LastTrack, so that it can take into account the non-equilibrium flow effects. The other one, of course, while we develop the code, we want to test and validate the resulting software by analyzing hypersonic boundary layer stability transitions. So although the main goal is to validate the software, so along the way, we will also do some research. So essentially, the work I'm doing here is to investigate the effect of mean flows on the stability analysis. So here's the two sides here. The first one is we use the LastTrack, use the default models of non-equilibrium flow. Then we use different mean flows from different CFD solvers. So we want to check how this mean flow will affect the result. The other one is still focus on the different models, but we kind of change the models that are used in LastTrack itself. The other way, in the second work, we use the same mean flow, but use different models in the LastTrack. So try to check the different effects. So this slide shows the governing equations of the LastTrack. So LastTrack is mainly based on the nonlinear parabolized stability equations. So if you check, this equation shows the nonlinear PSE equation. So you can see on this left-hand side, it includes the linear coefficient matrices. So essentially, I pick up this governing equation in this form is because in this way, we kind of can stand for the nonlinear PSE, linear PSE, and the linear stability theory in the similar form. For nonlinear PSE, we have this force interns. So force intern is okay. This equation is a kind of for Fourier mode in M and N. In one is in time, one is in the span-wise direction. So the nonlinear force intern include all these nonlinear things. And essentially, this is the coefficient matrix from the governing equation that included the nonlinear component that's here. So everything nonlinear is moved into this nonlinear force intern. So in that way, the left hand side, all these A hat, B hat, D hat, all these matrices only include the linear operators here. So with that, so that means when we consider the linear stability analysis, we just drop this force intern, right? And then so that's the simplification. So if you can see the governing equations for the LSD and the nonlinear PSE is just the left-hand side term. Of course, the LSD and the linear PSE itself, themselves, they have different approximations, right? Like the parallel flow effect that's included in the linear PSE. So with that, basically for LSD and the linear PSE, the A hat, B hat, D hat matrix, they are a little bit different. But in this way, from the code implementation point of view, we do not need to change a lot for the large drag code to extend its capability. So that's for the large drag. And here's a brief introduction of the mean flow solver that we picked up. So this is the CFD solvers that's currently available to me. Vulkan CFD is a cell-centered finite volume solver. It can handle both structured mesh and unstructured meshes. LoRa uses upwinding implicit algorithms, so it is structured multi-block code. So LoRa and the Vulkan, they are similarly they are publicly available to the US persons. And the shock fitting code on the other hand is a high order finite difference solver. It is a in-house code, so I have access to it. So as I mentioned, the main concern here is the effect of different thermochemical models on the stability analysis. So I first do the kind of a survey of the thermochemical models of various solvers I'm using. So in the stability analysis, basically there's a two-step procedure. The first step, we need to solve the mean flow. So it's kind of get a steady flow solution. And then the second one, then for the stability analysis, we impose a disturbance to the mean flow to check how this disturbance evolve when it propagates downstream. So last check here, we know last check is the code just for stability analysis. So essentially it's for the second step of the stability analysis. And these three code, they are for the mean flow calculations. I listed a lot of models here, but so these just show the default models that are used in the last check. And there's some comparisons here. So there's a couple things I want to mention. The first one is all these solvers include the last track. They are all based on the two temperature model. So we only have a translational temperature and a vibrational temperature. The other one is if you check the CFD solvers, the main differences exist in these models of internal energy chemistry or transport. if you can see, so the shock field code, we still use the harmonic vibrator model for the vibrational energy. The Vulcan and the roller, they use the CEA curve fit for the total energy. And in the chemistry, the difference existed in the equilibrium constant. So how this equilibrium constant is calculated? You can either use a curve fit, or you can use the minimum Gibbs free energy, like what we used in last track. And the transport properties, you can either use Yost mixing rule, or the other one is the Broadner's curve fit plus Wilks mixing rule. So that's the differences of the models. The following slide, I will briefly show you these differences. So as I mentioned, for the model of the internal energy, basically these solvers include the two types of models. The first one is just the total energy is just the summation of each energy mode, the transition rotational, vibrational, and that's basically the two energy mode is sum up. And you can see this is the model for the vibrational energy. So it's a harmonic oscillator model. This one is the CA 2002. So it's long curvilinear curve fit for the total energy and actually also there's formulas for the entropy. So that's the difference for the internal energy. The other one is the reaction rate. As I mentioned, the main difference exists in how the equilibrium constant are calculated. So this is a curve fit from Chu Park in 1990, and this is the equilibrium constant calculated from the free Gibbs energy. So I think the advantage of this model is that you could recall that the CEA model, they have the curve fit for the enthalpy and the entropy, so it's pretty straightforward. You just put this in two, and you get the equilibrium constant. Okay, so this slide shows the kind of the earlier model. It's the Browner's curve fit for species viscosity, and the mixture transport coefficient is come from Wilks mixing rule. So here you can see that's the viscosity, heat conductivity, and the heat conductivity relevant to the vibrational temperature. And a new model is based on, I would say another model is based on the Yost mixing rule. So this is here the transport properties of the mixture is calculated directly from the cross-section areas. So you can see there's no species viscosity, species conductivity comes here. So it's just directly calculated the transport coefficient of the mixture. So with that, I will show some preliminary results that we get. I want to mention that this work is still ongoing. So the case reported here is Mach 10 flow over 5-degree half-angle cone. So it included the mean flows obtained from the Vulcan CFD and the shock feed code. So this figure shows the mean flow comparisons of velocity and the two temperatures. So the red one, these two lines shows the translational temperature. These two shows the vibrational temperature. It's the x equal to 0.4 meter in the streamwise direction. So if we check here, the first thing we can notice is that here for the edge, boundary layer edge velocity, there's a small disturbance, small difference, but this discrepancy is kind of consistently exist, right? So very, so this discrepancy, we know it's coming from the different, because the solvers treated the shock differently. The Vulkan uses the shock capturing, and the shock fitting coder uses shock fitting algorithms. So that's of course the difference of the edge velocity. But the main changes, or the more important differences exist inside the boundary layer. If you check the peak temperature amplitude, peak temperature, you'll see the shock fitting code lead to a higher temperature inside of the boundary layer. So this is coming from the effect on the mean flow. And these two figures shows how so we use two different mean flows to calculate, to do the stability analysis. And this is on the left hand of this figure shows the result from the linear stability theory. So in here you can see the solid lines, they are coming from the shock fitting mean flow, and the other three lines coming from the Vulkan mean flow. So you can see it seems the in fact the curves move kind of a little upstream for the shock fitting mean flow. So this means the shock fitting mean flow actually lead to early instability in the flow. But on the other side, the maximum M factor is kind of lower compared to the Vulkan mean flow. This one shows the one result of the 700 kilohertz disturbance from the linear PSE. So it's the same thing here, right? But the red lines is kind of moving upstream. But in this time, it's the shock feeding code that lead to a large peak M factor, and also lead to it's kind of delay the instability a little bit. So so these figures show basically the mean flow from the different solvers actually do have a significant effect on the linear stability and the PSE result. The other one, as I mentioned, we also use the single mean flow. We just use the shock fit mean flow and use different models in the last track. One is the default models that are listed in the table, and the other one is we use the PAX model to calculate the chemical reaction equilibrium constant. So as you can see here, especially for the second model regime, the effect on the stability is these two results overlap pretty well. So it's when you go near the leading edge of the boundary layer or outside of the boundary layer, you have minor differences exist from the different models. So so basically that's the preliminary result I have. So here's the summary and the future work. So basically we know from these simple cases, the mean flows based on different models have a significant effect on the hypersonic stability, boundary layer stability. And then meanwhile, using different models in last track itself has a minor effect on the stability analysis. So my future work, the most important thing is, of course, to develop the last track code to finish the implementation for nonlinear PSE. Then I will also continue the work on the effect of mean flows, them to include both the linear and the nonlinear PSE. So we are planning to publish a paper at the next SciTech meeting with a more complete result. Thank you for your time. I'm open for questions.